prove by induction this formula. So this is what you want to prove. Okay? This is the expression, is a formula, so-called, you want to prove. Prove for what? For all positive integers n. So, if it helps you, you write down 1, 2, 3, 4, 5. Remember just now the 5 steps? So if it helps you, you can write 1 like that. 1 means let the Pn be something. Alright? Let the statement be what? Pn. Notice the question will never, most of the time won't define Pn for you. So you have to define Pn for yourself. And don't just stop here. You have to say that this thing you want to prove for all n, positive integers n. Okay, the question is given. Now, the second step is to consider the first case. In this problem, n, the smallest n is 1, so you consider P1. Okay, consider P1. And as I said in example 3, you better write this. This is important. Correct? This is important. Important for presentation. You cannot jump from here to here. You have to show that you are using the left-hand side. You have to show that you are using the left-hand side to get to half. The right-hand side, also, you have to show that you are using this right-hand side here and substitute n equals to 1. So therefore, P1 is true. Now, next step. Step number 3. Sorry, the handwriting was like that. 3. What is step number 3? Are you able to write? What is step number 3? You assume PK is true. Is that good enough? No, we cannot just say assume PK is true for what? For some K. Not for all K, for some K. For some positive integer K. Okay, for some positive integer K. Because you want to prove for all positive integers n, so we assume PK is true for some positive integer K. Now, to make things very clear, because when you say PK is true, what does it actually mean? We better write down what it means so that we can make use of it in the fourth step. We will always write this, i.e. K R equals to 1 over R. Notice, when we say Pn is this, Pk will be just changing the n to k. Don't go and change the r. Right? Don't go and change the r. Pn is this, Pk is changing n to k. That's all. Very simple. So, step number 4. We want to show Pk plus 1 is true. That means we want to show this. This is what we want to show, and we can see that this is the right hand side we want to get to. Correct? This is the right hand side we want to get to. So let's start off with the left hand side of Pk plus 1. What is left hand side of Pk plus 1? You look at the summation sign, I just replace k with k plus 1. Alright? Or rather, I replace n with k plus 1. Follow? Yes? Remember our statement. I better go back here. What is Pn? Pn is this. Correct? N. What is Pk plus 1? So I just change the n to k plus 1. So I go back here, k plus 1. Now, I say I cannot possibly exhaust all the cases, but if it's a summation problem, then very often we can use this trick. You sum from r equals to 1 to k plus 1. We will break it up and say, okay, I sum from r equals to 1 to k plus the k plus 1 term. This is what we call the k plus 1 term, this one. Correct? This is r equals to 1 to k, this is the k plus 1 term. What is the k plus 1 term? You just substitute r equals to k plus 1, you get this. Why do we want to break it up like that? Because if you look at this term carefully, this is this. Correct? And we now can make use of step number 3, which is the assumption here to replace this with this guy. Okay, so there is a blank here. I better write equals to. Okay, I better erase. No space. Sorry. You don't erase. I erase. Okay, 1 minus 1 over k plus 1. Alright, this is the most important line. This here to here is the most important. This replacement, this using step number 3 is most important. Correct? Once we make use of that, the rest is just algebraic simplification and aim towards the answer. Aim towards what answer? This answer. So we all know we need a 1. We already have a 1, so we leave the 1 alone. And then you combine these two fractions. Correct? You combine these two. What is the common denominator? It is k plus 1, k plus 1, k plus 2. Multiply numerator and denominator by k plus 2. Then you get this. Okay, I don't intend to go through a lot. Just after a while you will get it. Alright, we just read through and we will get this. All okay. Good. Now, let's not forget, I cannot stress this enough. Your conclusion here, the step 4 conclusion must be pk true, imply pk plus 1 true. Okay? Oh, sorry, need to write conclusion. This is step 4. Don't forget step number 5. Must write conclusion. Don't finish with step 4. You must write your proper conclusion. Step number 5 to what? Since P1 is true and PK true, imply PK plus 1 true by mathematical induction, Pn is true for all positive integers n. Okay, can? Question, example 5. Can press on. Quite easy idea, right? The rest is just example after example. Quite easy. Okay? Okay, this is the one that I believe some of you will have a little bit of problem. So can I seek your fullest attention here? This is combining the idea of recurrence with induction. I know recurrence is not your favorite topic, okay? But let's focus here. The sequence of numbers un is such that it's like that. Now let us interpret this guy, this one here. Let's interpret this one. What does it mean? It means u0 is half, u1 is half over 3. Correct? U2 is, this is 1/6, right? Okay. 1/6 over 1 plus 3, and on and on and on. Correct? This what does it say? It just means that by definition, by the definition of the recurrence relation, U0 is this, U1 is this, U2 is this, U3 is this. Now the question did not ask you to prove this guy. The question did not. The question says that this is the recurrence relation, this is the sequence where we are dealing with. The question asked us to prove by induction this formula. Okay? The question asks us to prove that formula. So we must be very clear what we want to prove. We are not going to prove the recurrence relation. The recurrence relation is given in the question. So that's why now step 1 becomes very important. When we define Pn, we say that let Pn be the statement Un equals to 1 over n plus 2 factorial for n larger or equals to 0. Now in this case, they give you this thing, they are quite kind. For n larger or equals to 0, you just copy. So let's be very clear what you want to show, what you want to prove by induction. I repeat, it's not the recurrence relation, it is this explicit formula that they want us to show. Usually it's like that. Usually they want you to show the explicit formula. Okay? Now, let's try. So let's consider this is step number 1, right? This is step number 1. Let's do, maybe I zoom in a bit more. Okay? Step number 2. Consider P, notice it's P0 here because you want to prove for all n larger or equals to 0. So the first case is actually P0. Yes, the first case is P0. So explicitly, left hand side here, what is U0? U0 is half. This is to be more, let's write this, given. Because U0 is half is given in the question. Yes? Given in the question, let's be very clear. Right hand side, substitute it explicitly. 0 into this, you get 1 over 2 factorial, you get half. So half, done. P0 true, done. Step number 3. Assume Pk is true for some k greater or equals to 0. What does it mean? Just means Uk equals to this. Step number 4. We want to show this left hand side equals to right hand side. Yes, we want to show left hand side equals to right hand side. Now, it's always easier to start with left hand side, aim towards right hand side, right? So we write left hand side of Pk plus 1 equals to Uk plus 1. Now, so far we have not made use of the recurrence relation. From step 1 to step 2 to step 3, we have not made use of the recurrence relation. This is the time to make use of the recurrence relation. Right? So we make use of the recurrence relation which is given. We accept it. Look here. This is the definition. This is definition of all this. So we can make use of this. For all n, this is definitely true. Nothing to prove, just use. So this is just Uk over k plus 3. Can? Just using recurrence relation. Okay, this is a comment. I write in red because not really you can't answer, but I better write this is using recurrence relation that is given in the question. Have we made use of step number 3? Not yet. So don't think we are so clever yet. Oh wow, we made use of something and then can find answer. Not yet. Because as with all induction, step number 4, we need to make use of the assumption. We have not made use of the assumption. So there is still one more line to go. in terms of making use of the assumption, we still have to use this assumption here. uk equals to 1 over k plus 2 factorial. Follow so far? So we make use of this now. Then we say, oh, okay, this is 1 over k plus 2 factorial k plus 3. This line is using step number 3, using the assumption. What is k plus 2 factorial times k plus 3? K plus 3 factorial, done. Can you understand? 12 factorial times 13 give you 13 factorial. Make sense? Need me to write? No need, easy enough. 12 factorial times 13 give you 13 factorial. Done. Therefore, equals to right hand side of pk plus 1. Okay? Therefore, pk true imply pk plus 1 true. So therefore, step number 5, since this is true, pk true, da 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 da. Okay, on conclusion printed for you. Okay, can? Quite fun, right? Quite fun, Fun. Example 6. Oh, yo, what did I just do? Okay, never mind, anyway, scrolling already. Scrolling.